Hi, I am Ms. Dinita Sharan from EEE Department, Tyagarajar College of Engineering, Madurai. In this video, the topic covered are operational amplifiers for arithmetic operations and operational amplifiers for wave shaping. First, let's see what is an operational amplifier. They are basically a voltage amplifying device designed to be used with components like capacitors and resistors between its input or output terminals. They are essentially a core part of analog devices. Feedback components like these are used to determine the operation of the amplifier. The amplifier can perform many different operations, giving it the name operational amplifier. Operational amplifier for arithmetic operations: adder, subtractor, differentiator, integrator, logarithmic and anti-logarithmic circuits. First, let's see about adder. An adder is an electronic circuit that produces an output which is equal to the sum of the applied inputs. An op-amp based adder produces an output equal to the sum of the input voltages applied at its inverting terminal. It is also called a summing amplifier since the output is an amplified one. The summing amplifier circuit is shown here. The KCL is applied at the node X, and then IF is equal to I1 plus I2 plus IF, and that is equal to minus of V1 by Rn plus R2 by Rn plus V3 by Rn. Then the output voltage is equal to minus of Rf by Rn into V1 plus Rf by Rn into V2 plus Rf by Rn into V3. A scaling summing amplifier can be made if the individual input resistors are not equal. Then the equation would have to be modified to minus of Vout is equal to V1 into Rf by R1 plus V2 into Rf by R2 plus V3 into Rf by R3 and so on. By putting all the resistance of the circuit above to the same value R, the op-amp will have a voltage gain of unity and an output voltage equal to the direct sum of all the input voltages, and therefore the output voltage Vout is equal to minus of V1 plus V2 plus V3. Non-inverting summing amplifier. By constructing an inverting summing amplifier, we can also use the non-inverting input of the operational amplifier to produce a non-inverting summing amplifier. AV is equal to V out by V in, and that is equal to V out by V plus, and that is equal to 1 plus RA by RB. And thus the V out is equal to 1 plus RA by RB multiplied by V1 plus V2 the whole divided by 2. If RA and RB are equal, the Vout will be V1 plus V2. Applications of summing amplifier. If the input resistance of a summing amplifier are connected to potentiometers, the individual input signals can be mixed together by varying amounts. For example, measuring temperatures, you could add a negative offset voltage to make the output voltage or display read 0 at the freezing point, or produce an audio mixer for adding or mixing together the individual waveforms, that is sounds, from different sounds channels like vocals, instruments, etc. before sending them combined to an audio amplifier. And the next application of summing amplifier is summing amplifier audio mixer, and the figure is shown here. Now let's see about subtractors. All operation amplifiers or differential amplifiers due to their input configuration, but by connecting one voltage signal onto one input terminal and the other voltage signal onto the other input terminal, the resultant output voltage will be proportional to the difference between the two input voltage signals of V1 and V2. The differential amplifiers amplify the difference between two voltages, making this type of operational amplifier circuit a subtractor, unlike a summing amplifier which adds or sums together the input voltages. This type of operational amplifier circuit is commonly known as differential amplifier, and the configuration is shown here. The output voltage is given by R3 by R1 into V2 minus V1. The applications of differential amplifiers are: it is used as series negative feedback circuit, it acts as voltage control circuit. The differential operational amplifier can be used as an automatic gain control circuit. Some of the differential operational amplifier can be used for amplitude modulation. And then let's see about integrator amplifier. Operational amplifier can be configured to perform calculus operations such as differentiation and integration. In an integrating circuit, the output is the integration of the input voltages with respect to time. An integrated circuit which consists of active devices is called active integrated. An active integrated produces as much as lower output resistance and higher output voltage than is possible. Integrated circuits have frequency limitations while operating on sine wave input signals. And the circuit is shown here. The output voltage of integrated amplifier is equal to minus of 1 by Rn into C integral of 0 to t V in dt. The applications of operational amplifier integrator. The operational amplifier integrator has many applications and uses, the most common of which is in the calculus operations. In analog computers, it is used as RAM generators, wave shaping circuits, and A or D converters. Another example of operational amplifier integrators potential application is the totalizer, a system that keeps track of how much fluid has passed by a sensor in a given time. Via mathematical integration, the operational amplifier integrator can convert waves, for example, square to triangle, triangle to sine, or sine to cosine. A differentiator amplifier. A differentiator amplifier is basically a high pass filter and are used in wave shaping circuits, frequency modulators, etc. An operational amplifier differentiator is an inverting amplifier which uses a capacitor in series with the input voltage. The operational amplifier circuit performs the mathematical operation of differentiation, that is, produces a voltage output which is directly proportional to the input voltage rate of change with respect to time. In other words, the faster or larger the change of input voltage signal, the greater the input current, the greater will be the output voltage change in the response, becoming more of a spike in shape. The differentiator works similarly to the integrator by swapping the capacitors and the resistors. The voltage, the output voltage is given by minus of Rf into C dV in by dt. Applications of operational amplifier differentiator. Applications of op-amp differentiator. Differentiating amplifiers are most commonly designed to operate on triangular and rectangular signals. Differentiators also find applications as wave shaping circuits to detect high frequency components in the input signal. Logarithmic amplifier. A logarithmic amplifier or log amplifier is an electronic circuit that produces an output that is proportional to the logarithm of the applied input, and the figure is shown here. The output voltage is equal to minus n into Vt, natural log of Vi by R1 into Is. Anti-logarithmic amplifier. An anti-logarithmic amplifier or an anti-log amplifier is an electronic circuit that produces an output that is proportional to the anti-logarithm of the applied input. And now let's move to the next topic, wave shaping for op-amps. Wave shaping circuits or the electronic circuits which produce desired shape at the output from the applied input waveform. These circuits perform two functions: attenuate the applied wave, alter the DC level of the applied wave. And there are two types of wave shaping circuits. They use clippers and clampers. Clippers. A clipper is an electronic circuit that produces an output by removing a part of the input above or below a reference value. Due to this, the peak to peak amplitude of the output of a clipper will be less than that of the input. Clippers can be classified into the following types based on the clipping portion of the input. Positive clipper and negative clipper. Positive clipper. A positive clipper clips only the positive position of the input signal. The clipping level is determined by the reference voltage V or F, which should be less than the input voltage range. The output voltage has a portion of the positive half cycle above V reference clipped off. And the input and output signal waveforms are shown here. Negative clipper. A negative clipper is a clipper that clips only the negative portion of the input signal. Diode D1 conducts when Vin is greater than or V reference, and therefore during this period output voltage VO follows the input voltage Vin. When Vin is less than V reference, the negative portion of the output voltage below or F is clipped off. And the waveform is shown here. Clampers. A clamper circuit produces an output similar to the input but with the shift in the DC level. In an op-amp clamper circuit, however, a predetermined DC level is deliberately inserted in the output volt. The clampers is sometimes called as DC inverters. Hence, the peak-to-peak amplitude of the output of a clamper will always be equal to that of the input. There are two types of op-amp based clampers based on the DC shift of the input: positive clamper and negative clamper. Positive clamper. A positive clamper is a clamper circuit that produces an output in such a way that the input signal gets shifted vertically by a positive DC value. And the waveform is here. The negative clamper. A negative clamper is a clamper circuit that produces an output in such a way that the input signal gets shifted vertically by a negative DC value. And the waveform is here. Applications. Microphone. It is used in microphone. Clippers prevents overdriving radio transmitter by voice peaks, and clippers can be used in voltage limiters and amplitude selectors. Excessive spikes above certain level can be limited or clipped in FM transmitters. One common application of the clamper is it is used in television receivers. Now let's see the summary of what we have seen in this video. First, differential and summing amplifier. By adding more input resistors to either the inverting or non-inverting inputs, voltage adders or summers can be made. The differential amplifier produces an output that is proportional to the difference between the two input voltages. Differential amplifier, the output voltage is given by Rf by Rn into V2 minus V1. For summing amplifier, the output voltage is given by minus of Rf by R1 into V1 plus Rf by R2 plus into V2 plus Rf by R3 into V3. And then differentiator and integrated operational amplifier circuits. The integrated amplifier produces an output that is the mathematical operation of integration. The differentiated amplifiers produces an output that is the mathematical operation of differentiation. Both the integration and differentiated amplifiers have a resistor and capacitor connected across the op-amp and are affected by its RC time constant. And the output voltage of differentiator amplifier is minus Rf C d of V in by dt. And the output voltage of integrated operational amplifier is minus of 1 by j omega R in C into V in. And logarithmic and anti-logarithmic circuits. An op-amp based logarithmic amplifier produces a voltage at the output which is proportional to the logarithm of the voltage applied to the resistor connected to its inverting terminal. And an operational amplifier based logarithmic amplifier produces the voltage at the output which is proportional to the anti-logarithm of the voltage that is applied to the diode connected to its inverting terminal. Wave shaping circuits. Wave shaping circuits are commonly used in digital computers and communications such as TV and FM receiver. Wave shaping technique includes clipping and clamping. In op-amp clipper circuits, a rectifier diode may be used to clip off a certain portion of input signal to obtain a desired output waveform. The diode works as an ideal diode, that is switch, because when on, the voltage drop across the diode is divided by one loop gain of the operation amplifier. When off, the diode is an open circuit. In an operation amplifier, clamper circuits, however, a predominant DC level is deliberately inserted in the output voltage. For this reason, the clamper is sometimes called as DC inverter.